I made a 3D printed planetary gear drive for a NEMA17 Stepper Motor. This one is a 2-stage drive, with a speed reduction ratio of 18.37 approximately. And this one is a single-stage drive with a 4.28 ratio. I tried to keep the design as simple and compact as possible, so let me show how I did it. I use this tool on my website. It's a planetary gear simulator that allows you to play with different variables, and it automatically calculates the gear sizes and overall ratio. I started by setting the module to 1. This determines the tooth size. Anything smaller than this will probably be too small to 3D print. After playing with the simulator for a while, you'll notice that you can get the most speed reduction by setting the ring gear. This will probably also simplify the mechanical design. I also noticed that to maximize speed reduction and thus torque increase, you want to keep the sun gear small, meaning fewer number of teeth, and the ring gear large, meaning larger number of teeth. So I set the sun gear to 14 teeth. If it is too small, then it will be more challenging to have a hole through to attach it to the motor shaft. The next step was to play with the planet gear teeth. By increasing this parameter, we see that the ring gear teeth increase, and the torque ratio increases, which is what we want. However, as mentioned before, I wanted to keep the design compact. So one parameter to look at is the ring gear root diameter. This will give you an idea of the outside diameter of the planetary gear drive. Considering that the NEMA17 motor casing is 42 by 42 millimeters, I did not want to make it much larger than that. So I landed on 16 teeth for the planetary gear, which results in 46 teeth for the ring gear, which at the same time results a root diameter of 48 millimeters. This will give us a torque increase of 4.286. With this information, I use this other tool I have on my website, the Gear Generator. This tool allows you to create the profile of external and internal gears, and then download them as DXF. So I just basically had to set the number of teeth, module, and pressure angle. I used 20 degrees for my design, and then I can download the DXF file. Then I can easily import this into SolidWorks or any other 3D software. After spending some time working on the mechanical design, this is what the assembly looks like. I am using M3 screws and heat inserts to put everything together. 3mm bearings to mount the planet gears, and one large 30mm bearing to mount the output plate. The 2-stage drive has a very similar design. It is basically two 1-stage stacked together. And I decided to use 2mm ball bearing in between stages to allow smoother rotation. In both cases, I created two designs for the outer piece to be mounted either axially or radially. Then I made some basic torque tests to measure the efficiency of these drives. I am using this pancake-style stepper motor. I measured the torque of 0.15 Newton-meter, which is very close to the advertised value of 0.16. My test setup consists in pressing slowly against a kitchen scale, then recording the max value. I am using a 0.15 meter long lever. For the 2-stage planetary gear, I noticed the 3D printed brackets starting to bend, so I think I could get a higher reading with a more rigid setup. In any case, these are the results. For the 1-stage drive, I measured a torque of 0.61 Newton-meter, which means an efficiency of 94%. On the 2-stage drive, the measured torque was 2.2 Newton-meter, which means an efficiency of 80%. Perhaps these results can be improved by adding grease or lubricant to the drive. I will make the files available on my website if you want to print these yourself. I am also in the process of designing a harmonic drive and compare its performance to this planetary gear design. Let me know if you have any suggestions.